So one of my earliest memories is sitting in the front seat of the car with my father, driving on a long stretch of highway, a beautiful, bright day, blue sky, and I turned to him and I asked him, "What is God made of?" And I think that moment is a memorable landmark for me because of his reaction, where he turned to me with mystery and awe and said, "I really don't know." And shaking his head, looking out to the horizon, we kept on driving together, and my eyes went up to the clouds again, and I reflected about that question and what it meant. I've always wanted to know how things work, and there are no limits. Nothing is off limits. How do things work? This curiosity led me to begin thinking about the foundations of thought and feelings. How is it that a countable number of neurons chattering to one another in our minds, sounds like a machine, could generate the fluid buzz of our existence, of our thoughts and feelings? How could parts turning upon parts generate all that we know as we sit here right now? That curiosity led me to the world of information and computation. And for several decades now, I've been pursuing AI, principles of computational intelligence. Now, you might say that what it is people in my field do is pursue an aerodynamics of intelligence. What are the laws and principles to explain intelligent thought and behavior? Now, many innovations have come out of this work over the last 50 years. Quite impressive pieces of work on computer vision, systems that can see, systems that can interpret natural language processing, reasoning, decision-making. Many of these things are actually currently in our lives. If any of you use a GPS system to navigate, the A-star algorithm used to find paths through a very, very large search space came out of the field of artificial intelligence. Now, one big area that's exploding these days is the area of machine learning. The explosion is in some ways linked to the explosion of data coming into our lives through the web, through cheap sensors, through all the capture we're doing in healthcare, for example. And the idea is we have algorithms that can run over all this data, more data than human beings could ever look at, and build predictive models. And these predictive models can be used, for example, to do diagnosis in healthcare, or predictions of the future outcomes, in both cases better and deeper than any human being can do. Now, you might say that, and I say that, we're in the early dawn of a computational revolution. But I sense there's an inflection point in the capabilities we're seeing in the systems that we're building and in our prowess with understanding. There's a long way to go. But there's an acceleration towards more intelligences with more capabilities in our lives that are coming of our own hands, of our own work. And this may be frightening to some people. I understand that. But my view is that these methods will come to surround people in a very supportive and nurturing way. These methods will complement the intellects we're developing, will complement our own human intellect, and empower us to do new kinds of things and extend us in new kinds of ways according to our preferences and our interests. So I find it a very exciting time, and the prospect for humanity very, very exciting. Now, one thing that I've been looking at and very interested in is in thinking about the complementarity of machine intellect and human intellect is to think about methods that would allow computational systems to understand people better, understand our needs, our wants, and our minds. And in some work early on at Stanford during graduate school, I was very interested in applying some of these predictive models in time-critical areas like trauma care and aerospace. In fact, I spent quite a bit of time coming down to Johnson Space Center down in Houston, where I basically modeled the space shuttle propulsion systems and built predictive models that could take all this streaming sensor data from the shuttle and fuse it and generate inferences about what might be going on. In particular, of course, in Mission Control Center, what might be going wrong. But while I was doing that and working on these base level models that I thought I set out to do, which I, of course, was very happy with in terms of how they performed, I noticed that there was a challenge for the people sitting in Mission Control Center, the flight engineers. The overwhelming amount of data they would look at of streaming sensors as they would try to interpret what was going on, even given the help of our inferences from our computer programs. And we begin to build models that could automatically trade off the complexity of the information for the relevance, highlighting the most important information for the specific engineer given their background and training. So we were building models of human beings, turning the power of these methods we had built for systems, for healthcare challenges, propulsion engines, to human minds, running them in parallel with those first kind of base level solutions. And I was really impressed with the elegance of how these systems could reason about people and make systems really closer companions, more complementary to people. This led to an area of work over 15 years of thinking about human cognition and its nooks and crannies and biases and blind spots. And a lot of this has been studied for decades in the area of cognitive psychology, where we've characterized some of the nooks and crannies quite well. And these are repeatable across people, even though we're all different in our own ways. And the dream I had was, could we develop automated systems that would know people so well, whether it be in the area of decision-making, attention and multitasking, memory, problem-solving, visualization, many others, that the systems could work to extend people in a very personalized and very supportive manner. So let me talk a little bit about decision-making first and judgment, which is a very deep area of psychology that we looked at very carefully, and it's an area that we've studied with our algorithms that do learning and reasoning about people. In particular, what we do here is that, to give you a sense for how this works, is we imagine a doctor, for example, or a NASA flight engineer looking at data, like symptoms of a patient or the space shuttle sensors, and coming up with a set of beliefs, probabilities, what's going on, I'm not sure which system is failing here, but I have different probabilities represented by this bar chart here. Meanwhile, we have a system that has taken all this data in, that knows so much more in certain ways, but in more narrow ways than people, and it's making inferences about the world, about the space shuttle engines, for example. They might be different. Here's where the magic comes in. We work very hard as computer scientists and psychologists with building systems that predict what humans will be thinking. They might not be perfect, but we try our best. And then those probabilities are considered by the automated system together with the base level gold standard of the best it can do, and that is used to inform people, to remind people, to make sure they're not surprised. Now, speaking of surprise, a really fun area for me we call surprise forecasting. It's kind of a crazy idea. If I ask anybody in the audience here to think about what surprised you the most in the last 12 months, let's think for a moment. It could be private, personal, or something you saw in the public press. You could do the same thing 2 years ago and 3 years ago. That's a database of human surprises for you. And the idea in our work was, let's pick some domains and do some surprise modeling and automate a surprise forecasting system that could be helpful to people, especially when it comes to avoiding bad surprises. The stuff we kind of worry about at night that maybe even make us a little fearful. What you see up behind me is GPS data. We have about a million kilometers of volunteer GPS data of the Seattle highway system and surface streets, as well as millions of more miles, not shown here, of all the sensor data coming from the Seattle highway system. And based on that data, about a decade ago, we built a system that could predict with a model for machine learning what the future of traffic would be across Seattle. And on a little smartphone would put up a little clock at different parts of the town. And you saw, for example, there's 10 minutes left until that clog will melt. People love this. But we noticed that very often people in Seattle who fashioned themselves as Seattle traffic experts sort of knew what was happening anyway. So we thought about, can we build a surprise model for traffic that would really be useful as a demonstration of surprise forecasting? And so we created a system that would store up a database of human surprises, very rare events, that actually, if you backtrack through the event, you'd see what was going on in Seattle. There was a strange accident way up north that caused rubbernecking, and for some crazy reason we don't understand for the dynamics, there was like no traffic on the ever-clogged 520 bridge. This strange anomaly, 1 in 500. But when you have a decade of data and millions of miles of information, and you fuse that with weather, major events, traffic accident reports, our system knows more. And so we have a database, and here's the cool thing. For every surprise in the database, we go back 30 minutes or an hour until things were normal. And that's our training case. When we do machine learning, we learn a surprise forecasting model that when it runs, you can tell your app on your smartphone, only bother me when I'll be surprised in a half hour on my commute home. Otherwise, I'm not going to look. And the surprise model runs in parallel with a base model, just like at the NASA Mission Control Center, what we're doing there. Now, the surprise forecasting work is quite generalizable. And in fact, we're recently now applying this to healthcare. So one of the most joyous days in the lives of families is bringing home someone from the hospital, as captured by this beautiful graphic here. A recent study showed that in 20% of cases, discharged patients are readmitted to the hospital within 30 days. It's very expensive and costly, and it's not exactly clear what's been going on with, for example, why they were discharged and would come back so soon. We built systems, one in particular, with 10 years of hospital data, looking at 22,000 variables that people could never look at with their own eyes, to build a base system that would predict when this patient being discharged now might come back within 30 days and give the probability to the physician at discharge time. But and I should say, those models are now running as we speak in hospitals across the world. However, we went further and thought, many physicians, as you know, are a confident lot. They get trained, they see lots of patients. We thought, wouldn't it be kind of interesting to build a surprise forecasting model, for example, an emergency department physician? And we can train up the model on absolute surprises to physicians. We have enough data to do that. When it runs, it basically says, this patient you're discharging now will likely come back within 3 days with a primary diagnosis nowhere in the current chart. Do you want to take a peek? And that's how that works. Now, another area that we've done a whole bunch of work in is memory. If you think about it, we all have shared memories, especially when we're in the same room together. We have shared short-term memory. We all know together about Faith's talk just now, for example, and other talks today we'll be hearing. We can refer to them, we can point at them. We also have shared long-term experiences that we can point at together and ground with family members, with college buddies. I thought years ago, wouldn't it be kind of nice if you could walk with a computing system the way you walk with a college buddy, and you can refer to the same events. Remember the time Jim fell out that window after that long night out? and you laugh together. Because I know that she knows or he knows, and they know that I know, we have that shared memory. With a system called Life Browser, we train up a system on lots of data to understand what are the most memorable photos, desktop activities, internet browsing experiences, meetings on a big timeline that you've had, and provide a volume control. Show me more, show me less. So the system actually is like a companion family member that's been working with you all this time, and we can use that in search and in retrieval. This shows you a little bit of Life Browser here. There's a volume control at the top. You can really turn up and turn down. And we can also click on pictures. Behind the scenes is a memory model that's learned from my own training data that understands my memory for meetings, pictures, and so on. And by clicking on a graphic, machine-learned models are bringing up beautiful, emotional pictures because the system understands my life and knows about a July 4th, where I had a memorable time 12 years ago. And that's my son back then. He's now 16. But that memory comes up as a shared memory the way a family member would say, remember that time on that July 4th at Whidbey Island. On attention, it's another rich area of psychology and work for us. What is it that we attend to at any moment? How deeply invested are we? What's the cost of disruption? If I come out of a task to take a message, an alert, a text, a pop-up on my screen, how hard will it be to get back into what I was doing? Can we have systems that understand that? And with patterns of attention, we even have been using vision in social settings to understand who's talking to who, what are different people's goals, such that a system could come forward and be part of the social situation, as I'll show you in a second. So we've combined some of these models, sometimes 4, 6, 12 different kinds of models of people together, wrapped them in a package to understand what integrative intelligence might be like. Maybe intelligences are coalescences of a constellation of predictive models about people and other things in the world. And we added vision and speech and natural language. Let me show you a system we call the receptionist, which is at once running a number of models, but I want to highlight here attention. A red dot you'll see is the attention of an artificial receptionist as it tries to help people schedule a shuttle to go across campus at Microsoft Research.
Do you need a shuttle?
Yes.
Which building are you going to?
I forget, where are we going?
I think it's building 9.
You sure?
Yes.
So, you're going to 9, right?
Yes.
And this is for both of you, right?
Yes.
I'm making a shuttle reservation for building 9 for 2 people. In case you want to correct anything, say or press star over.
Okay.
Are you visiting someone?
Okay,
Yes.
So I think
I'll
everything should
help
be
you
all set.
register in just a moment.
Fabulous.
Okay.
I think we're set.
Okay.
Excuse me, sir.
Yes?
You will be on shuttle 53. It should be here any second.
All right, thank you.
So by my door, my morning report looks like this. I walk into work in the morning. Here's what I see.
Hi. Hi, Eric. No one has stopped by to see you since we last talked. And Outlook Mobile Manager is still down, so I'm not seeing messages from your email. Catch you later. Bye-bye.
We have an assistant here who's reasoning about 10 or 11 things about me. How long it'll be until I'm back. Will I attend a meeting on my calendar? When will I get to email next? How busy am I? Where am I likely to be on campus? Where will I go to next? And who might be coming to my office? Let me show you how that works. But I want to basically, that was the outside view looking in. Let me show you inside looking out at Johanna, an intern at Microsoft, who hadn't been to my office before, was trying to make an appointment, was a little bit nervous. But what I see in Johanna's eyes, in this case from the point of view of the assistant, as we call the system by my door, I see humanity in her eyes. The humanity of all of us as we come to work with these systems over time. And these current versions, I admit, are clunky. Here's Johanna.
Hi.
Hi.
Are you here looking for Eric?
Yep. Yes.
Eric is talking with someone.
I can
and
see
this might
that.
take a while.
Oh.
But I don't think he'd mind a brief interruption right now. Would you like to go now? Okay. You could check back in 15 minutes or so, and we can see if he's available then.
Okay.
Another option, we could set up an appointment. Would you like me to check his calendar to see if he has any free time later today?
Yes.
All right. No, his calendar shows that he's fully booked today. I'm not sure, but I don't think he'll be attending the meeting on his calendar today at 1:30 p.m. I could pencil
That's
you in
like
then.
now.
Would that work for you?
Sure.
Great. Would
Great.
you like me to write this on his calendar?
Oh, no.
Okay. Feel free to stop by at that time, but I'm not
Wow.
certain he'll be
This is
here.
amazing.
Yes, I'll see you later then. Bye.
Nice meeting you.
So it's going to go well, I think, at the end. Let me just say that it's not about only in-your-face intelligences, but also these systems will creep into the seams and help us out in a variety of ways as they slip into the seams. The same platform that the assistant is using is being used behind the scenes in an elevator project we call the third-generation elevator, where it's learning to track the nuances of steps over time in a very highly trafficked area where most people don't use the elevator. And when we turned this thing on to be like a Star Trek experience, ordering the turbolifters, people were at first surprised. But over time, there was a kind of coevolution of learning and knowledge between the system and the humans. And this magical elevator experience appears. And you see at first people are quite surprised. But within a few days or weeks, we had experiences where people just sort of walk into the elevator as if it was the bridge of the Enterprise. And it's the assistant platform here that's doing that work. So let me just summarize by saying we're now seeing methods that combine both human and machine intelligence in new ways to learn how to weave them together in one project, exploring the heavens together, where, for example, we use machine vision and human perception together as a team that's unified by principles of learning and decision-making to explore galaxies, millions of galaxies that haven't been explored before because there are too many of them for human attention alone. And moving ahead, I'll summarize by saying I'm very excited about the prospects for people of what this will mean. These systems will be serving us and extending and empowering us. And most of all, I think, and the most important goal for me, is to seek a deep understanding of who it is we are. I think this is the most important goal humanity has. So I'll stop there.